So today, let's just do some quick review. So here's a flashback from derivatives, and it's going to come into play today. We're going to talk about this. This is the chain rule, which says if I want to take a derivative of a function inside of a function, so f of g of x, very simple. Take the derivative of f, which is f prime, plug in g of x times the derivative of g prime. Or basically, it's the outside, take the derivative of the outside, plug the inside in, times the derivative of the inside function. And we'll see today that since antiderivatives, which are closely related to integration, are essentially it's the opposite of derivatives, and well, the chain rule must have some equivalent association for integration. And we're going to talk about what that is today. So that's why we talk about this here. Now, I wrote down these. Again, these are our basic formulas for doing antiderivatives. So we can take the antiderivative of x to the a, 1 over a plus 1, x to the a plus 1, plus a constant. Don't forget the constant. The antiderivative of sine, or the integral of sine, is negative cosine plus a constant. The antiderivative of cosine is sine. Antiderivative of secant squared is the tangent. Antiderivative of secant times tangent is secant. Antiderivative of 1 over 1 plus x squared, what a really awesome function that is arctangent x. And then I threw on one more. Now, these ones, these 6, are things that we can take antiderivatives of. Now, there's one function we can't take an antiderivative of, but we can actually say something about a definite integral. Because remember, we have two kinds of integrations. There's the indefinite, and there's the definite. And the indefinite integration is antiderivatives. And the definite integration is you're measuring something. So this integral, 0 to 1 of the square root of 1 minus x squared dx, is 1/4 pi. And I like to use this one a lot just because it gives us just a little bit more flavor. And it's something that we can actually say what the formula is, because if you remember what the square root of 1 minus x squared looks like, well, that's simply the top. Well, okay. Okay, I'm really feeling like drawing circles, which is bad for my next example. Okay, let's try this again. Okay, let's pretend that's a circle. This is the square root of 1 minus x squared. It's the top half of a circle, and if I'm integrating from 0 to 1, I'm finding this area. And of course, we know that the area of a circle is pi r squared. So this is 1/4 of a circle with area 1, so it's 1/4 pi. So this is our sort of like one lone exception. So ultimately, if we're going to deal with any kind of problem where we're asked for an integration, we're going to come down to using one of these things here. Either we get it into one of these 6 things where we actually know what an antiderivative is, or we'll be dealing with a definite integral that involves something like this. And that's pretty much all I can ask you to do this quarter. Now, next quarter, you'll get to do more, which will make it even more exciting. You're not going to be limited by just these things. We're going to do a lot more stuff next quarter. And that's next quarter. We should do what we can do this quarter. Now, what we talked about last time was we looked at the definite integral from a to b of f prime of t dt, and we said that this is f of b minus f of a. Now, this is not very shocking at all. This is our fundamental theorem of calculus. And if you think about what this is saying, f prime of t is the rate of change. And this says, well, if we know the rate of change between x equals a and x equals b, if we know how fast we're changing, then we can find the total change, because f of b minus f of a is the total change. And this is the question we talked about on the very first day of class, that the fundamental theorem of calculus ties these two together. If I know how fast I'm changing, I can figure out what my total change was. So the reason we like to use f prime here is we think of it as a rate. So there might be a word problem. I think there's some word problems in your homework where it talks about we know the rate at which something is happening, how much is the total. And in other words, it's just referring to this formula. So since this is really the fundamental theorem of calculus, it's not very exciting. Another way we can say this, of course, is if I want to know what f of b is, and if I know what f of a is, and I know how much I'm changing, how fast I'm changing, well, to find f of b, I take f of a plus the integral from a to b f prime t dt, which, of course, finds me my total amount of change. Okay, so that's not very surprising. Let me do one quick example to show you how this might work. So let's look at the volume of a sphere. Now, one way I can think about making a sphere is I can start with just a point, which is essentially a sphere with radius 0, and I can just slowly blow it up. Imagine it's like a balloon, where you're filling it with air, and it just slowly gets bigger and bigger and bigger and bigger. So if I think about the balloon, or the sphere here, so I have one sphere, and then what I'm going to do is I'm going to make a slightly bigger sphere, just by increasing radius just a tiny amount. So I have something that looks like this. So I take my sphere, blow it up just a tiny bit. How much? Very small change in r. You might say delta r or dr. Now here's my question. How much did the volume change? Well, if we think about it, I can take the volume, and I can think about the difference is I essentially take the surface area. And I'm just blowing up the surface area by just a little tiny bit. So how much does the volume change? Well, it's the surface area of the sphere, which I'll abbreviate SA, times the change in radius. Now, this is not exact, but the smaller the change in radius is, the more exact it gets. So if I think about the sort of the instantaneous change in volume, then this becomes exact. So the change in volume is the amount of surface area times the change in radius. So if you think of it here, it's just because, well, you just take the surface area and you just blow everything up by dr. Just add a little bit extra layer. Okay, are you convinced about the picture? Well, okay, we'll pretend like you are. We'll keep going. Okay, so let's say we're convinced. All right, now, it would help if we knew what the surface area is. And it turns out that there's a formula for that. So the formula for the surface area of a sphere of radius r, so let's just say this is a sphere of radius r, is 4 pi r squared. For example, Newton was able to show this, and he was able to show that surface area of a sphere is 4 pi r squared without doing any calculus, using geometry. All right. So here's my question. Suppose I want to know what the volume of a sphere of radius r is. Well, according to this, I can take the volume of a sphere of radius 0, and then I just see how much did the volume change as I went from 0 to r. Because this is what this bottom formula tells us. It says if I want to know what my function is at some point, I take the function at some point which I know. In this case, 0 is something I know. And I just say how much did it change. Now, what is the volume of a sphere of radius 0? 0. Yeah, there's nothing there. There's no volume. Well, okay. What do we know about the change in volume, dV? Well, we have something here. This is 4 pi r squared dr. Now, 4 pi is a constant. Comes out. So r squared dr. What's the antiderivative of r squared? 1/3 r cubed. And I mean, notice here that when we talked about antiderivatives over here, we used x. There's nothing special about x. We can always change the name. In fact, that's going to be the whole point of today, is that we can change the name. So the same rules apply. So this is 4 pi times 1/3 r cubed, which is the antiderivative of r squared, evaluated from 0 to capital R. Now, notice when I plug in 0, I just get 0 out. So that my final result will be 4/3, because I combine the 4 and the 3rd, times pi times capital R cubed. So what they have that the volume of the sphere is 4/3 pi r cubed. Now, if you've had any geometry before, you already knew this formula, but now here's sort of a proof. Next week, we'll do another proof for finding the volume of the sphere, which uses sort of a different technique. And we'll get the same answer. So this is just sort of some intuition about how you might be able to use this. Okay. Now, how do we actually go about doing integration problems? Well, the way we do all our integration problems so far is we essentially take what we have and we work on it. We manipulate it. We change it. We use various things. We might use trigonometric identities. We might use just factoring things, expanding things, rewriting things. Always our goal being to get it down to one of these. So our goal is always simplify, simplify, simplify until we get down to one of these, and then we can say, now we can do something. So today we want to add sort of a new tool to our arsenal of doing integration, and it comes from this chain rule for derivatives. So this chain rule for derivatives is going to become something for integration. And it's known as the substitution rule. So let me just quickly write down the chain rule again. It's the same thing I have up there. So if I want to take the derivative of f of g of x, it's equal to f prime of g of x times g prime of x. Now, how do I turn it into something for integration? Well, very simple. I just take the integral of both sides. Now, what do I get when I take the integral of the derivative of f of g of x? Well, what do we know about integration and differentiation? They're essentially like the opposite, almost like the inverse, up to within a constant. So if I were to integrate this side, I would get essentially f of g of x. So we're going to have something equals f of g of x, and namely, we will have that the integral f prime of g of x times g prime of x dx, space, dx, is equal to f of g of x plus c. So this is really nothing more than just take the derivative of each side and just simplify. And just remember, the fundamental theorem of calculus says if I have a derivative and I integrate it, I get back what I started. So in this case, the integral of the derivative is f of g of x. So here's a very simple example. Suppose I want to integrate cosine of x squared times 2x dx. How could I do this? Well, I look at it and I say, well, it really seems to match this kind of format here, where I have this g of x. I can think of this x squared as g of x. And notice here, 2x is g prime of x. And then what is f of x? Well, f of x is cosine. Well, I really should say f prime of x is cosine to put it into this format here. So according to this, well, it's simply I take the antiderivative of cosine, which is sine, of x squared, and I add c. So I'm just literally applying it here where I say, I know what g is, I know what g prime is, I know what f prime is, then I just plug it straight in. Now, usually it's not so simple as that. Usually we have to do more work. And so this leads us to what we call, in general, u du substitution. And the way it works is it says if I have f of g of x times g prime of x dx, what I can do is I can rewrite this integral. Notice I'm not using f prime anymore. I'm just saying, just in general, we can rewrite this. And the way we write this is we say, well, I'm going to let this inside part, we're going to call that u. So u is g of x. And then what I'm going to do is I'm going to say, well, what is du dx? Well, du dx is just the derivative of g of x. It's g prime of x. Or put another way, du is g prime of x dx. So that this will become the integral. I just do some simple substitution. F g of x becomes u times g prime of x dx. G prime of x dx becomes du. And essentially, it gets rid of clutter. So if we were to go over to the case there where we had the integral of cosine x squared times 2x dx, if we just went through and did the substitution, we'd be saying u equals x squared. And then I take the derivative of both sides. We can save ourselves a step here. Essentially, we just say du is the derivative of g of x dx. So du is the derivative of x squared is 2x dx. We say, here we go. There's u. Here's du. So this is the integral of cosine of u du. So it just simplifies things. It gets rid of clutter. And now that I've gotten rid of that clutter, I say, I see it. That's the integral of cosine. And I have a formula for the integral of cosine. And now I say, well, that's simply sine of u plus c. All right, now there's a few things that we have to do, though. Because the problem was we didn't start off looking for a function of u. When we started off, we had everything in terms of x. So when we end up with a function, what should it be in terms of? It should be in terms of x. So we say, well, that's okay. after I get past my integration, I just remember that u equals x squared, and I replace it. So this becomes sine of x squared plus c. All right, so let's just make a few comments, and then we just do tons of examples. I mean, this is how you master this. Is you just do it over and over and over again. So first off, what's the clue that we want to use substitution? Well, if you think about the chain rule applied when we had a function inside a function. So substitution is great when we have a function in a function. That's observation number one. So that's often a good clue about what you're going to do. If you see a function inside of a function, substitution is going to be one of the best things to try. Now, there are other things that you can try, and you'll learn about them next quarter. Substitution is always the best thing to try first off. Now, at the end, don't forget to replace the u by g of x. Because when I start off, I wanted to find the integral of cosine x squared to x dx. In general, I need to get back to the same variable I started with. In this case, I need to start with x. So don't forget, after you do your integration, you need to you do u equals x squared, you simplify it to something that you can handle, you actually do the real integration, and then you just work your way back to get back in terms of x. So don't forget to replace the u by x squared. Okay, some other comments. Here's another comment. Our goal is always to make things easier. Or I like to say simpler. So if you try a substitution and things are getting more complex and not simpler, you probably did the wrong substitution. You should try something else. Now, occasionally it happens that it gets worse before it gets better, but that's very, very rare. Now, the other important thing to do, and the last comment, and then we're just going to work through, excuse me, a bajillion examples, is make sure you replace every x by a u. I should say not by you, but by something with you. So, for instance, here, I have the cosine of x squared 2x dx. When I get here, I want absolutely no x anywhere. I have to get it all in terms of u. I can't mix x's and u's together. So if I had gone into this and there had been an x cosine u du, I'd be in trouble. It wouldn't work. I need to get it all in terms of a single variable. So in this case, the important thing is, where do I have x? I have an x here, I have an x here, and I also have a dx. So I have to make sure I get rid of these x's and I make that dx into a du. So all the x's have to become u's. Pretty much as long as you remember this, you can do any problem that we throw at you. So let's just start throwing up problems, and we'll see how far we get. Any questions about this before we start? Very clear? Ah, excellent. Of course, the best way to do this is to do 100 of these. We don't have the time to do 100 of them, so we'll let you do some in your homework. So here's a simple integral, 1 plus square root of x, quantity squared dx. Now, if you had this integral to do on, say, homework or even on a test, what would you do? What are some ideas? Now, you could try substitution, but in this case, it's probably easier just to say, well, look, I know how to take something and square it. That's 1 plus 2 root x plus x. Because I just square it. I know how to square stuff. A squared plus 2ab plus b squared. And then I say, well, the integral of 1 is x. What's the integral of square root of x? Well, to do that, think of square root of x as x to the 1/2. So I'd multiply by 2/3, because what I do is I raise it to the 3/2, because I take a half plus 1, which is 3/2. Then I multiply by 2/3. So that's 4/3. X to 3/2. And what's the integral of x? A half x squared. Okay. So this is probably very simple to do. It's the same idea. We just expanded, and then we broke it into three small, simple things. Now, what if I ask you for this? What's the integral of 1 plus square root of x to the 100? Ah! Now what do you do? Okay, well, what can we do? Well, 1 plus square root of x times 1 plus square root of x times 1 plus square root of x. And 25 pages later, we've made a dozen mistakes at least. And then we can integrate. Seems very bad. We'll almost surely get the wrong answer and waste too much time doing the test. So let's think about it. Maybe we can do a substitution to make this easier. Now, if I look at this, what substitution makes sense? I come to one of these rules here. This is a useful thing to remember. Substitution is great. I can't even read what I wrote here. Okay, I think I said substitution is great when we have a function in a function. Because remember that substitution comes from the chain rule. So if I want to try substitution, the thing to do is look for a function inside of a function. Now in this case, do we have a function that lies inside of another function? Yeah. We have this. Now I could use square root of x, but let's just go for the whole shebang here. Let's call this function on the inside u. So u is 1 plus square root of x. Now let's figure out what's going to happen. So here I get du. Now 1 plus square root of x is another way of saying 1 plus x to the 1/2. So what's the derivative of 1 plus x to the 1/2? Well, the derivative of 1 is 0. The half comes down, x to the minus 1/2 times dx. So that's the change in u. So now I say, okay, this is great, because what I'm going to do is this is going to become the integral of u to the 100, and that seems a lot nicer. And I just have to figure out what to do with the dx. Now the problem here is before, when I had dx, I was able to also have, if you remember back over here, with the cosine of x squared, I also had that 2x dx. But here, I'm missing this x to the minus 1/2. Okay, we have to account for that. That's okay. We can figure this out. Let's see what we can do. What I need to do is I have to figure out what dx is in terms of u and du. Let's solve for dx. What is dx? Well, I'd move the half over to the other side, so that would become a 2. I'd move the x to the minus 1/2 to the other side. What would that become on this side? I move this x minus 1/2 over here. It becomes x to the 1/2 r square root of x, and then du. So this is nothing more than just sort of switching the order and multiplying this to the other side. Nothing very profound yet. Now, what do I know about square root of x? I'd like to replace that in terms of u. Can I do it? Well, I come back up here. And I see that I say here, u is 1 plus the square root of x. So if u is 1 plus square root of x, what is square root of x? U minus 1. Aha. So occasionally what you'll have to do is you have to play around with it and figure things out. In this case, we have to work with it until we got to a point where we could express du in terms of dx. Now, we got lucky over there because we already had our 2x dx set up there. If it's not there, you have to play around with it. But now we're in great shape because we say, okay, I replace this by u. This became u to the 100. dx becomes 2 times u minus 1 du. And now I feel much more confident about doing this kind of integral than about this kind of integral. Because what does this become? Well, the 2 comes out. That's a constant. And then this becomes u to the 100 times u is u to the 101 minus u to the 100 times du. Still have the 2. All right, what's the integral of u to the 101 du? Well, it's going to be u to the 102. We add 1 to the exponent. and times it by 1 over 102. Then we still have the same 2 there. I'm just going to carry it through. What's the integral of u to the 100? U to the 101, because we add 1 to the exponent, and then we times by 1 over 101. And what else do we need? C. Yeah, because this is an indefinite integral, so don't forget your plus c. Now, are we done? No, we're not done yet, because at the end, don't forget to replace u by g of x. Don't forget to essentially substitute back, because I wanted to start with something in terms of c. Okay, well, we're really close. So this will become 2 times 1 over 102 is 1 over 51. And then I just replace what u is. U is 1 plus root x. So 1 plus root x to the 102 minus 2 over 101, 1 plus root x to the 101 plus c. There we go. And this was much shorter than trying to actually multiply out 1 plus root x to the 100. You can do it, but as I said, more likely than not, you'll make a lot of errors. But here, we didn't make any errors. Or at least we don't think we did, because we didn't have enough time to make an error. It was too fast. Okay, all right. You're not impressed yet. All right. We'll keep going until you get impressed. You're like, wow, that one's so cool. Okay, so let's do some more. All right, so suppose I ask you to integrate x squared plus 2x divided by x cubed plus 3x squared plus 9 squared dx. So now let's suppose we ask you to do this one. Okay, so we're looking for substitution. Substitution says look for a function inside of a function. So does anything pop out to us? That's being a function inside of a function. Yeah, the denominator, especially this piece right here. This pops out to us as being a function inside of a function. Say, okay, that looks like a really strong candidate. Let's try it. X cubed plus 3x squared plus 9. Okay, if that's u, what's du going to be? 3x squared plus 6x, and the derivative of 9, of course, is 0, dx. Then the dx is multiplying by the whole thing. Now we look at it and we say, okay, let's cross our fingers and hope that we have a 3x squared plus 6x somewhere floating around. We look upstairs and say, ooh, we're really close, we're really close. Because upstairs we have an x squared plus 2x, which is really close to 3x squared plus 6x. In fact, how close are they? Yeah, they're off by a factor of 3. And constants are like, no problem. We love that. Now, there's two ways to approach it, depending upon how you learned it. So one way to think about this is I can factor 3 out, and I get x squared plus 2x dx. Now, what you can do is you can come up here and put a 3 here. But if you put a 3 here, you change it. So what do you have to do? Put a 1/3 somewhere. Oftentimes people put on the outside. Then you say, okay, now I'm ready to substitute. The other way you can do it is you can just say, well, look, I'll start with this relationship here, and then I'll just divide both sides by a 1/3. So that I get x squared plus 2x dx is 1/3 du. Both ways give you the exact same answer. So whatever way works best for you, do it. Whatever way you'll remember, that's the way you should do it. So let's see what happens. So the x squared plus 2x dx becomes 1/3. The 1/3 is a constant. Let's pull it out. Du. What does the denominator become? Yeah, it becomes u squared, because our function is this inside piece. So over u squared. And can we integrate this? Well, what's another way to write 1 over u squared? u to the negative 2. Yeah. And now we're like, okay, now we're starting to cook with gas. Now we know what to do. Because here we have this wonderful rule of how to integrate something to a power. X to the a dx, which works the same way as u to the a du. And we say, okay, piece of cake. I don't even have to think anymore. I just will use the rules. So I add 1 to my exponent, it becomes u to the negative 1. And I divide by negative 1, which is the same as multiplying by negative 1, by the way, plus c. Okay. Or if you like, this is negative 1 over 3u plus c, because I can think of u to the negative 1 as 1 over u. And what's our last step? Yeah, I've got to replace u. So I write what u is. U is x cubed plus 3x squared plus 9. We're done. All right. Okay, let's try this one. This is a good challenge. The integral of secant x over secant x plus tangent x. Anyone have a favorite number? 8. Okay. 8 dx. See if we can try this one on for size. That looks kind of weird. Now, next quarter you can actually learn how to integrate secant x. And we can't do it now. We don't have the tools. We're so close. We're only 2 sections away. But you have to wait till next quarter. Okay. Well, what pops out? What seems a good candidate for being our u? Yeah, the secant x plus tangent of x. That makes a really strong candidate for u. Okay, so let's let u equal secant of x plus tangent of x. So we take the derivative. Of course, this requires us to remember various things about secants and tangents. What's the derivative of secant? Secant tangent. What's the derivative of tangent? Secant squared. Okay, and that's all times dx. Of course, we don't have to remember too hard because it's basically kind of hidden over here. Now I look at this for a second and say, oh dear. Because I don't have secant x tangent x plus secant squared x on the top. All I have is a lonely old secant x. What are we going to do? It sounded like somebody said factor out a secant, but even if they didn't, I'm going to say that's what they said, because that's a great idea. Secant x, if I factor it out, because notice that both of these have a secant x here. So I'm going to factor it out. Okay, that's fine. Now I say, okay, well, I have a secant x dx. That's great, because here it is. But what about this? What can I do with that part? It's u. Right. It's just really u, just backwards. U is secant plus tangent, but really secant plus tangent. This is an old great trick. It's tangent plus secant. No surprise. Okay, so this is secant of x times u times dx. Or I can write this as secant of x dx is 1 over u du. Okay. Now we have something we can work with. So what does this integral become? Well, the denominator just is u to the 8th. That's easy. So I just replace that secant x plus tangent x by 8. What does the secant x dx become? Well, we have it right here. 1 over u du. Okay. Now we have something that's a little bit easier for us to handle. Now, what's another way for us to write this integral? Yeah, first off, notice I can combine u to the 8th times u in the denominator, and that's u to the 9th. So this is u to the negative 9 du. And now we're back where we were before, where we have this integral of something to a power. Piece of cake. All right. So the rule says I add 1 to the exponent. So that's u to the negative 8 times 1 over the exponent. So 1 over negative 8 in front. Plus, of course, c. We don't forget our c. Or I feel like this is negative 1 over 8 times u to the 8th plus c. And finally, our last step, replace u by secant x plus tangent x. And there we go. Piece of cake. All right. So far, all we've done are indefinite integrals. We should talk for a second about definite integrals. So how do we do definite integrals with substitution? Well, you have two methods. We'll do both of them, just to let you decide which one you like. Now, they both work, although some work a little bit better than others in certain settings. But they both work. Method 1. So remember that a definite... What? Did I make a mistake?
What happened with dx?
Where? The dx became that 1 over u du. Because I have the secant x dx is 1 over u du.
Oh, okay.
Good? Aha! Aha! A light bulb has come on. Good. Okay, so two methods. One method is, remember we're a definite integral. Definite integral is we integrate from a to b. And so we're looking for a number. An indefinite integral is we're looking for a function. So method 1 is forget that it's a definite integral. Do the indefinite integral. All right? Now what you do is by doing the indefinite integral, what do you end up finding? You find an antiderivative. Well, after we have the antiderivative, then it's very easy to do the definite integral by using the fundamental theorem of calculus. Because once you have the antiderivative, to do the definite integral, you just plug in the endpoints into the antiderivative. Okay? That's method 1. Method 2. Do the definite integral. But here's the important thing. But make sure to update the boundary, or the endpoints. Now, why do I say that? Well, we've been a little bit lazy in some respects. Because when we talk about the integral from a to b of f of x dx, what we really mean to say is it's not really a to b. We really mean to be very specific. It's x equals a up to x equals b. That's what we mean when we talk about going from a to b. It means we're going to let x range from the value a to the value b. Now, let me rewrite this in terms of substitution. So in substitution, we would have f of g of x times g prime of x dx. And our substitution would be u equals g of x. And our du is g prime of x dx. Okay? And so the inside part, that's very easy. That's what we've already been doing. That simply becomes f with u plugged in times du. Because I replaced the g of x by u. And I replaced the g prime of x dx by du. But remember one of the things I said. When we're doing substitution, we have to change every single occurrence of x. It has to be replaced by u. These also correspond to x values. So I have to change them now to correspond to u values. How do I do that? Well, it's very simple. If x equals a, I come into here and I say, what is u? Well, plug in a. So it goes from g of a, because I just simply plug in a. And then, again, same thing. When x equals b, I come down here. And I say, well, if x is b, what is u? Well, I plug it in. So it goes to g of b. So that's the two ways you can do definite integrals. So you can either make sure you change to an indefinite integral, then at the end use the fundamental theorem of calculus, or you just you do the definite integral and always make sure to update your bounds, your a and your b. Okay, which method do you want to try first, 1 or 2? 1? All right. So to do 1, I have to be careful to make sure I pick the right thing. Okay, so suppose I ask you the following. What is the integral from 0 to 1 of x divided by 1 plus x to the fourth dx? Okay, so to do this, if we're going to use our first method, we say, well, let's forget about this problem for a second. Let's just do the indefinite integral. So drop the bounds. Now, here, it doesn't really make sense what to do right now. Because if you let u equal 1 plus x to the fourth, then we're going to get something x cubed dx. And that's just not going to work for us. So I would probably give you a hint if I were going to ask you this question. Here's my hint. 1 plus x to the fourth is the same as 1 plus x squared squared. Now you can say, oh, we can see where Professor Butler is going. Favorite function coming up. I can tell. What's our substitution? Let's make u x squared. What does du become? 2x dx. And then I can use my fancy whiteboard. A half du is x dx. So that this is the integral. The x dx becomes a half. I'll just pull it out in front, du. In the denominator, we get 1 plus u squared. And we look at this and say, well, I wonder if we've seen this before. We have. In fact, you don't even have to look very far. It's right up here. That's arctangent. What a cool function. Ah, I feel warm and fuzzy inside. Now, we have to, at the end, of course, go back in terms of x. So this is a half arctangent x squared plus c. So we've done the indefinite integral. Now, the reason we do that is the fundamental theorem of calculus says to do the definite integral, just find any antiderivative. Woohoo, we got one. And evaluate at the endpoints. Now, in this case, this is the general antiderivative. What should c be when we actually come up here to evaluate? What should we choose for c? It's a trick question. It cancels itself out. So we can choose anything we want. So let's choose the easiest thing we can think of. What's the easiest thing we can think of? 0. Okay, so we choose 0. All right. So now what we do is we have, well, look, to integrate this, we find find the inverse, find the antiderivative. I knew I'd get to that word sometime. And evaluate from 0 to 1. And now, that's very nice. This is 1/2 arctangent of 1 squared minus a half arctangent of 0 squared. And we know these values. Arctangent of 1, this is all on your sheet, by the way, of things you'll know on the final. Arctangent of 1 is pi fourths. Arctangent of 0 is 0. And so we end up with our final answer, pi eighths. All right. So here's an example of one way you can do it. Now let's go through and do another example. Suppose I ask you the following. Find the integral from 0 to pi halves of cosine theta times the square root of 1 minus sine squared theta d theta. Now, there's lots of ways we could do this, but let's just try to do it the way, try to read my mind. What am I trying to get you to do? Use substitution, yeah. What's a good substitution? Well, notice on the outside, here I have a cosine theta d theta. And I think to a second, and I say, what function, when I take the derivative of it, gives me like a cosine theta d theta? Sine does. And I have a sine inside of here. So here, let's try sine theta. And notice the reason I choose that one is because, again, on the outside, it's exactly geared up with this cosine theta d theta, such that this would become the integral of square root 1 minus u squared du. But I'm doing a definite integral. I need to figure out my bounds. So originally my bounds were from 0 to pi halves, but these are in terms of theta. So I need to figure out my bounds now in terms of u. All right, well, if theta is 0 and u is sine theta, what should u be? Well, it should be sine of 0. What's the sine of 0? It's 0. Okay, that was easy. If theta is pi halves and u is the sine of theta, what should u be? It should be sine of pi halves, which is 1. And now we say, okay, so doing this integral, which looks kind of messy, is the same as doing this integral, which, well, it's still messy, but maybe it's something familiar. Maybe it's something we've seen before. Maybe it's something written on the board, perhaps. I don't know. What does this integral turn out to be? Yeah, this is pi fourths. Exactly. Because we got it down to an integral where we don't know what this antiderivative is. I don't know if you'll ever know. Depends on how far you go. We don't know what this antiderivative is, but we know what the area is. And we know integrals represent area. So if we can find the area, then we can do the integral. Okay. Let's see. Let me just make one other quick comment. So a lot of times, suppose I know that the integral of little f of x dx is capital F of x plus c. What can I say about the integral f of ax plus b dx? So I know this is true. If this integral, the integral of little f, is capital F plus a constant, what happens when I replace the inside by ax plus b? Well, we can actually go through and work it out. U equals ax plus b. Du is a dx, right? Or, just move that to the other side, 1 over a du is dx, such that this becomes the integral fu 1 over a du, but the 1 over a comes out. And what is this integral? Well, this is, according to up here, this is simply nothing more than capital F of u plus the constant. And then I just replace what u is. So this becomes 1 over a times capital F of ax plus b. And then, of course, plus our constant on the end. So in other words, if we know how to integrate x, and then all we do is we just basically scale x and add a constant, then I know how to do the same kind of thing. And you should be able to do these ones without even having to think. So much so that if I said something like, what's the integral of x plus 9 to the 5 halves? Well, it's really just the same as saying if you did u equals x plus 9 and went through the work. But it's really the same as saying roughly the same as u to the 5 halves or x to the 5 halves. We know how to do that. So this would be you add 1 to the power 7 halves, and you multiply by 1 over that new power. Of course, add a constant. Or what if I asked you what's the integral of sine of 2x? So again, this is the form ax plus b. And again, we could go through the whole thing, but we should, hopefully after you do this for a while, you'll see that, well, I know the antiderivative of sine, is negative cosine. And then I plug in my 2x. And then the only thing is I have to account for that 2x, because essentially that 2 is acting as the a. So what do? I multiply by half in front. So, and with some practice, oftentimes when you have something very simple things like this, you don't even need to make substitution. Just with practice, you'll be able to do it automatically. Okay, that's it for today. I will see you on Friday. Woohoo!